So good morning, everyone. I'm Christoph Zeihsel, Head of Operational Excellence in Applied IT. And I have some 20 plus years of experience in the field, seeing firsthand how good information generated out of data can totally transform operations. And today I'll show you how with RTM Pro you can do just that. So let's get started, and I'll look forward to bringing our manufacturing analytics skills to the next level. In the background, there is my colleague and data scientist, Blanca Hernandez, in the Q&A section, where you can post some questions and she will try to answer them right away or later if necessary. First, we talk about the origin of Applied IT. Where do we come from? What are we doing? Then some powerful tools that we have developed over time in order to match our portfolio of method and tools. We will then talk about the ramp-up Applied IT method, where we can start at any point within an OEE of a certain production and overall equipment efficiency and elevate it to a higher level. We will then see this firsthand then in RTM Pro on a live demo where I'll show you how to analyze, but also create the first actions in terms of OEE improvement. Then we go back and look at a method for complex problem solving, which is called Do It Applied IT. And back into RTM Pro, we will solve a quality problem that may occur in any kind of production. And in the end, I'll invite you to join us in Cadiz for a workshop, but I'll tell you more about that later. So about Applied IT, we are funded from a team with more than 25 years of experience in complex problem solving. And they had the method, and now they also need the tool in order to progress in any type of problem as quickly as possible. As you can imagine, the moment you call the fire brigade, the fire is already ongoing, and that's just what happens to us every time. So we are optimized in solving problems much faster than any other method and without the profound need of subject matters expertise. And to do so, we have divided into 3 business units or branches. The first is the data application customization. Those focus on providing the tools that are essential and necessary for the team, but also our customers in order to be successful. Then we have the data engineering services, where we are able to quickly integrate any type of data in any environment. So ETL services, so to say, because it's important to grab food quickly to progress on data-driven decision making. And then there is the application of that, which is my team, the operational excellence, where we apply our own solutions to help customers to evolve, but also, of course, customers can provide those services for themselves just using our software tools. We have worked in many countries over the last more than 25 years and completed over 100 projects. And I tell you, especially on the problem solving side, that so far we have not found a problem that was not solvable. And we have therefore a big variation of customers in automotive, but also other industries that are trusting our solutions and services in order to improve their own operations. Let's talk about products. We have several products. The center of our universe is RTM Pro. RTM Pro is the manufacturing analytics tool which just helps us to improve OEE and problem solving. And that's exactly what it does. Without the need of additional back knowledge. We have established a second RTM Lite, which is a a dashboard on steroids, we could say, because we are combining the visualization part with the analytical part and offer it on a web-based solution to be able to still have visualization with, let's say, basic analytical tools in order to have first or second level analytics, even through that interface. We also have transfer for process mining. So we see parts flow and for logistical improvements, which are also heavily needed on any shop floor. And we have defect map, where we focus on identifying where the defects are, clustering those, generating useful data out of these defects tracking that later can be combined with process and customer data for a real powerful combination and information generation. And we have the function model, which helps to track processes and projects. And this helps us ourselves to really follow the flow of a project. Today, however, we focus mainly on RTM Pro and manufacturing analytics. So what is it? It is an in-database analytical platform. It works basically on a simple SQL database, and it will not store any data, any information out of that database. So there's no black box solution. Everything is already calculated in place. It also is very simple to use, as you will see later. It is not only for the statistics superhero, but also for the engineer, the quality engineer, without, let's say, IT expertise or a master black belt in statistics. Anyone could use this software in order to progress into a proper solution, combining it with a method. So asking the right question, performing a method in combination with a tool gives it the real power. And for this, we have developed three, basically it's more than that, but those are the methods I want to talk about today. One is the do it applied IT, the problem solving method. We're going to talk about that a bit later. And the pre and ramp up. Pre-ramp up is before an SOP, so the preparation already at the customer side, where we review design OEE capabilities, but without an interlinkage of the line. And then post SOP is ramp up applied IT or ramp up AIT, where the focus is on assessing or starting either from an SOP level, that means from zero production to the target, which usually could be about 75% OEE. But the beauty of this method is that it can start anytime. Depending on where we are on our OEE improvement ladder, we can start at any step and have the right tools and method to just progress from our defined starting point. And we have applied that already many times in the last couple of years and found that there is a vast benefit of using a method and data-driven approach, especially in a ramp-up, which can save you 17 weeks in average. If you apply a pre-ramp-up, that means if the engagement, if the method and the progress already starts on the design or post-design of a line, and then even if we start later after SOP or at any point of the OEE level, we clearly can still catch up some time, as you see here in the gap, to conventional ramp-up approaches. And then in the end, there is again a potential saving out of this, which of course transfers directly into cost savings and return of investment that are usually way below 1 year on those kind of projects. So what is it? The ramp-up is in different phases. Each phase has its own tools, its own methods, and its own approach. And we apply those approaches in the specific areas or in the specific ramp up windows or OEE windows. For example, the R phase, the readiness phase, is happening in the sample production. And the M phase is the longest one. And in the M phase, you always see the saddle, the stagnation of the ramp up briefly, because you are in a transition between a sample production and a continuous production. And even though you technically are already advanced where you're supposed to be, the operations cannot yet fully follow the new established line takt. So you will always see that. And in the beginning, you might panic, and we also did, until we realized that this is a perfectly normal stage, and we identified the things needed in order to get out of this as quickly as somewhat possible. And we have done this in several projects. Just one of those is represented here with a project in Germany, where we, in the very early stage, avoided claims with some heat paste application, with claims coming back from the customer. We successfully generated and worked through more than 25 projects. That is not a very huge number. The key is here to always focus on what is needed to be done right now. And we're talking here 3 to maximum 5 projects that really move us forward, keep the team motivated, and ensure success in a very short time frame. We have then saved a lot of time, of course, with performance improvement tasks, and have generated or multiplied the output by 21, and boosting the OEE with 50% points in the 9 months this project was running. But let's now go from the theory and look into a demo line, and I demonstrate you in RTM Pro on how we approach ramp-up projects and what are the key tools we use there. At the beginning, you shall know that there is 5 stations we are looking at. So we have the first station, we position a circuit board into a housing. Station 2, we press this circuit, the cover onto that housing. Station 3, we put 2 screws into that cover in order to fix it in place. Station 4, we perform a leakage test, which is just a high pressure and sustain test. And this is a duplicated stations. That means there's 2 leakage test stations that are running in parallel in order to cope with a lower cycle time per station, but still matching to the align cycle time. And same in station 5, the end of line test for all the functionality of that combined or already product. So let's go into RTM. I have it open here already. What we see here is I have selected a time frame, which is just a few days in July, but that's sufficient for what we need to see here. We see here all these 5 stations that I just explained to you and the functionality. Within those stations, we have the variables that are available for this particular database. We see in black the numerical values, we see categorical values in blue, and we see time values in red. We see here that we have 2 timestamps. One is indicated the checkout and one is indicating the check-in, which benefits us in a later stage here. Let's start at the very basic. We want to know the OEE. So let's do an OEE gap analysis. First, we need to tell RTM which are the good parts. I have here a parameter called yield, and a yield of 0 means bad, a yield of 1 means good. I have set this up in the settings, and now I just tell it what is the good stuff. I have here a target. I put in 5400. Why? Because it's calculated from the target cycle time and the planned operation time during the time frame I have selected. And with recalculate, I then have the complete overview about OEE. What do I see here? I see the target, which I obviously selected as theoretically produced part in the selected production time. And in the end here, I have the yield, which is nothing else than the good parts that left the line. And only with those two, I calculate OEE. So I divide the 1,878 by 5,400, and I reach an OEE of about 35%. So if we look back into our method, we are just at the end of the A phase and we are entering the M phase. What is happening there is the line starts to be interlinked. We before saw more one station running, the other one stopping, so it's more a stop and go. And we start a first flow, but very, very slowly at the beginning, and progressing into a more stable line takt in the end of phase M. And that also explains why the lost time is rather high, because we still have a lot of stations pushing and starving in between. So that is nothing that should bother us too much in that particular level that we are currently in. We see quite a high number of quality rechecks. We will look into that later, but let's get started on the performance. And in order to do so, I show you how we look at performance or cycle time. I start the CTT, which is cycle time over time, on the screwing station. So this is how a CTT looks like. We have here in the x-axis 24 hours of time selected. In the y-axis is the time itself in seconds, and each and every part is a representation of the time between one part to the next part. So that's the checkout to checkout, if we want to stay in that language. Also down here, we have dots that have only borders, and those is the check-in to check-out time, and therefore a direct representation of the process time itself. Means that we have the process time down here, we have in between the changeover time, and we have the part-to-part time up here. Also down here, we see boxes that are representing a gap, a time gap between two parts, which is lost time. We always set a trigger for lost time at 3 times the target cycle time to really clearly differentiate between performance and availability. Only with this clear threshold, it is possible not to mix those two. And by the color representing the time, we see on how long these downtimes were. If we would connect also maintenance data or machine data, we could click into those boxes and then see what happened during that time. As an example, during those 28 minutes, there was a break. Up here, we see the number of parts produced during that hour. So we are looking at about 30 parts to 39 parts as a maximum during that 24 hours. And here we see a histogram, which already gives us an indication that something strange is going on here, because we have 2 populations of cycle time for this single station. Now let's look at the most important information for us. And that is here on the right-hand side, the P10 value. It is here with about 65 seconds is the P10 lower than the P50. What is P10? It's the 10 percentile of cycle times. That means 10% of the parts run at that speed, which is about 65 seconds, whereby 50% or the median of parts run at about 90 seconds. So you have a clear difference between the median and the P10. And this is why we use those values to identify a localized cycle time, or a cycle time for that station, the capability of the station itself, which obviously is between 61 and 64 seconds, and the capability of that station being interlinked with the surrounding ones, which is basically increasing that cycle time to almost 90 seconds. That also directly answers the question, is that station a bottleneck? It obviously is not, because it could do much faster. It's held back from somewhere else. Let's look at another example, positioning here. When we open up this CTT, we see the distribution looks completely different. We have a very clear histogram here on the side. We have P10 and P50 leveling at about the same level. This clearly indicates that this is most likely a bottleneck, but let's see that later in the combined view of all stations. So this graph gives us performance, clear, and availability, represented in the lost time minutes, in that case 372 minutes altogether. So that's already two components of the OEE. So the only missing one is the quality, and that's what we look at right now. So we go to quality analysis. We again say one is the good stuff, and now we see a total overview about the parts that ran through that station, which is 2075. And that's the number of parts, not the number of cycles. You can differentiate between cycles and parts here. We only look at part level. And we have the first time serials. That is basically the first pass yield, first time those parts ran, they directly came through. We have the repeated OK. Doesn't make sense, but for some reason, some parts ran multiple times, even though they were good the first time. We have recovered serials, started bad, ended good in multiple runs again, which reduces the total capability because it uses line time. And we have the total NOK serials. That means the actual scrap parts produced in the selected time frame. So this is concluding then on the quality. But we're still at a station level. Now let's combine all of what we've seen so far on the full line. And in order to do that, I want to show you some improvements. So let's get started with the beginning of the week, because we want to see the difference from the beginning to the end of the week later. So I start here and I run the OEE components. OK is the good stuff, already indicated correctly. And what I see now is I start here, I have performance. On the performance, I have P10 and P50. As I said, the two most important values for us. And directly looking at that graph, we see that we have one primary bottleneck, which is the positioning, because P10 and P50 are about the same level. And we have a secondary bottleneck, technical bottleneck, on the leakage test, which is also having a potential of 79 seconds down to the next bottleneck 66 seconds. So immediately we can tell what's the benefit. If I work on this bottleneck, I have a gap of 5 seconds. So that is my true potential. Everything I touch here will benefit the whole line. Then here I have the first pass yield is 100% here, and lower on the end of line station with a first time quality of first pass yield of 88.4 and the last time quality or last pass yield of 88.7. And down here I have the availability giving me the lost time in minutes for each and every station. So that is the beginning of the week. It really gets interesting when we compare our progress, if we see on what happens if we change something. And in order to do that, I click on compare data, and I have saved the end of the week before in a CSV file, which I'm opening right now. And now I see both information combined together in one graph. And obviously that week I was working heavily on the performance, because we have a significant improvement in performance of the positioning as well as the leakage tester, with a direct impact not only to the station level but also to the line level or interlink between station or P50. What I also see is the next thing I need to do there. There's obviously a logistical bottleneck here between pressing and screwing. So something is going on in the handling of the parts because the station can do faster. Still, we don't get the parts through. And that is my next task. Go to the line, identify what's going wrong in the handling of that part, and gain these benefits, level the P50 where it's supposed to be, which is about 65 to 70 seconds here. So that's my next topic on performance. On the lost time, it has actually increased. Why is that? Well, we have improved the performance, but we have not yet directly improved the output as we see here. So stations are waiting longer. And so this should not bother us at this moment in this phase, but it's still important to notice. What is bothering me, however, is a decay of quality here in the end of line. We started already bad and we ended the week even worse. So that is definitely another big topic that we should look into, and that's what we should do right now. So let's go back and filter the whole week again to see the whole week time frame. Then I have here one parameter that is called Q rate last 100, which is just, remember the yield is just a 0 and 1. So I have a running average of 100 parts, which directly represents the quality rate in a moving window. So when I double click on that, I see that parameter in a run chart. I change to time view. Still something's odd here. I obviously multiple information within that same graph. And as you remember from the presentation itself, you know that there is multiple stations involved. So what I do now is I select this one as a category, I select this one as a Y, and I look at it as a Ys per category, separating the two categories, which is station. And now I see it in the right way. And the picture is now clear. I have a fluctuating quality in station 1, generally better than station 2, but also not where it's supposed to be. I have a critical decay of quality in station 2, which only starts to improve on the 12th of July around 7 a.m. because then it increases back. But that's not where we stop. We want to know what happened in station 2. Why was it bad? Why is it good now? And for this, we can use the tools already available to us in RTM. So I take the box select. I say that's the good stuff up here. That's where I want to be. And I say, this is my blue group. And I select this down here. This is where I don't want to be. So it's my red group. And I run a group analysis, which is separating those parts by the serial number, creating an information, a statistical information for me on which parameters are involved in the separation of those two groups. Here also it takes into account categorical values, which can only be up to 16 values. So that's the information shared here. My categories are only 2 because station 1 and 2, so that's easy be accepted. And now I have the potential candidates of driving my quality in station 2. I filter by p-value, so 0 is the good stuff, means high significance, and together with a high end count, it gives me the, let's say, best statistical result. You see some of those and you immediately know that you just need to look at those two areas. So that's about the statistic you need to know for that. There is some information that is not quite useful. The process completed, so timestamps and quality rates. I knew that because this is where I selected it, right? But the first here is interesting. So it looks like the main driver could be, that's the hypothesis, the current on no load, because there's a clear differentiation between the distribution of the blue and means the good stuff to the red means the bad parts. So that could be the main driver. But that brings me into quality. I don't want to go down that path for now because that concludes the ramp up itself. Let's go back to the presentation and look at a possible or look at the method to solve any possible quality problem. I remove my filters. Later, we're going to look here at station 1. Why? Because as we saw already, it ran way more parts than the other one. So I apply here a filter. I say station 1 only, save and close. I save everything and I go back to my presentation. So that was how we look at and how we can analyze with RTM Pro on OEE. Now let's look at problem solving, which is much more specific. That's why it's the main method that we are using. But I started with ramp up because it's more general, the application of that method, so to say. And in the problem solving, the first and most important step, let me get some laser pointer again. The first and most important step is the define. We always say a problem well defined is a problem almost solved. You need to know what is your driving parameter, what is your KPI you identify your problem with. Don't go with feeling, don't go with estimates, facts and figures, a data point or a combination of multiple data sources. Then you run an observe, you do an MSA to really identify or qualify your stations itself or your measurement system. And you start with a contrast diagram, which then results in a fault tree, giving you an indication on what is important and what is not. Once you have done that, you go deeper and investigate the hidden root cause by eliminating everything that is not important. And you just scratch it out. You don't look at it anymore. You focus really on what is driving my why, what is driving my problem, and forget everything else. Then, once you have converged to a suspect root cause, you test it. Only if you are able to switch a problem on and off, you can be sure that you actually have identified a dominant root cause. And this is what you want to tackle. And this is what we do in the apply phase. We apply the corrective action. And in the IT phase, we ensure that we perform all the necessary countermeasures in order to ensure that this problem is not occurring again and is already caught before it is made an actual problem. So how are we thinking that way? So most of you most likely know Ishikawa because it's one of the, let's say, standard problem solving tools. We always ask there on what is wrong or how does it work. The problem with that for us is that you need expert knowledge. When we come into a problem solving project, it's likely that we have seen something similar before, but most of the time we are not the subject matter experts. So we are focusing on something else. We are focusing on a fact-based problem solving where we are converging. So as I said earlier, we identify the why, we identify the problem, and then we backtrack from there and eliminate everything that is not essential by asking only one question: that what is different? What is different between a bad part and a good part, between a better part and a worse part, between a higher level of a certain value to a lower level of a certain value? And by asking that question, and that is exactly what RTM is made for, we are sure that we quickly converge towards our root cause candidates, which later we test and we implement the countermeasures and ensure that it is solved permanently. So another case study I'd like to share with you is in Romania. Project duration here is 5 months. During those 5 months, our approach was mainly on problem solving. And we had a couple of stations to focus on. One is cell pressing. oil filling, helium test, end of line. And we were able to significantly improve in all of those areas. So cell pressing reduced significantly. That's the default tree for this particular problem. We identified that there is a difference depending on where the issues occur, and then quickly could converge into a permanent root cause to avoid that issue. And this is how those fault trees usually look like. Some are more slim, some are wider, but it's just to document everything we go through. And that's the most important thing. Always keep the North Star inside. Means when you run an analytics, when you run manufacturing analytics, you need to have a good question, and you need to walk through and always think about that questions, not get distracted by any other interesting things that may arise to you. You want to answer that questions, and this is where you go to. This way we could also eliminate entirely rework in oil filling, and we have identified and eliminated some other root causes in end of line and helium test. So let's go back to RTM and solve one problem. There is a field return with this serial number that we might want to look into. So I close the presentation, and I copy that number to here, and I click the search button. Search button here means I have a serial number, I put it into the system, and RTM will search all available data independent of every filter that I have set. If that part ran 3 years ago, if it's in my database, it will find it, and it will show me every information that is available to this part. So I see here in which station it was present. And here in the end of line, I, for example, see that this part ran twice. First on the 12th, and second also on the 12th, but on a later time. And I have the information of both of those runs. Now let's look on when it was that part was at those stations. So now I see it in a time view. I see the actual time of that part from check-in to check-out, which are those 38, of course, seconds. And I see the transition time. Let's zoom in a little bit more into that area. From one station to the next one, with a longer transition time, obviously, between screwing and leakage test. Now let's go back to autoscale, because I also see here that I have run it through end of line before 3 a.m. in the morning, and then again after 6 p.m. in the evening. So in between, most likely, this part was out of the station and then came back from an analytics, or anything could happen to the part, and it ran again. But that's, again, not where we stop. So now we know what were the values, and we know when it was in which station. But we want to know what is special with that. So the special event search takes the value of that part and compares it with a normal distribution of all the parts that ran during that same day, and see on where this part is different, where it comes out of that normal distribution. So we see here, as an example, in the station itself, end of line, the working current of that part was higher than the normal distribution of other parts during that one day. So that could be a significant information to me to identify what went wrong with this part. So now let's double click. Let's double click on this value, and we see the run chart of this, where is it? Working current here, working current, and the part is marked in that run chart. What immediately catches the eye is that there is more parts that are, let's say, abnormal in that area, and this is where my investigation leads next. But before I do that, I want to see what are the actual bad parts in here. So what I do is I create a filter and I say, I want to filter all the bad parts. And now I want to give those bad parts a color. So I use the radar function and I give bad parts orange color. Orange. Apply to all, save and close. And now I put on recalculate and I see the bad parts in orange color. Maybe it makes more sense if I don't see it in a part by part view, but in a time view. So I click the change here and I clearly see that there seems to be a limit here and here that are effective to be for the parts to be good or bad. So let's put that limit in the graph. And now I have them in as lines. Of course, I also want to see on how many parts were bad considering those limits. So I take out the filter here again. I want to see all the parts. And now I want on the working current, I want to run a process capability. And the process capability gives me a clear feedback on the lower limit and how many parts are, let's say, slipping out of that lower limit and how many parts are bad because they are exceeding the higher limit with number of parts, but also in percentage. And when I scroll down here, I see that the CP and CPK for that process, considering automotive requirements, are not capable. So there's clearly something that needs to be done here. The limits I introduced earlier in the run chart are globally valid. So these are the exact same limits that also are active for this function. But let's go back here. There is now a couple of things that we could do. Let's go this way. And we could do, for example, a group analysis. We can just select here and say, yeah, that's the good stuff again. That's the bad stuff again. And now run some analysis on it. But we've done that before. So let's do something different. In this case, I want to show you a pair analysis. A pair analysis is a more needle approach to problem solving because it immediately answers the question, what is different? And in order to see what is different, we always have a good and a bad part, a bob and a wow. And that's exactly what we want to do here. So I click the selector and I select a good part and I say, this is 1. So it's my 1 category. I go back to my, let's close this one. I go back here and I say, this is to this good part, the bad part, or the red part. And then I select another one, 1 and 2, another one, 1 and 2, and a last one, 1 and 2. And they all appear now here in the pair analysis. I can also use the pair analysis if I have multiple parts that came back from a customer. So I can here say import data, and I have then this saved as a pair analysis. I open it, and then I have these pairs coming into my graph, immediately being able to analyze them. If I say recalculate, I find everything that is essential for those pairs to be separated. And that is, in that case, on the table end of line, the working current, which is, yeah, not quite surprising because this is where I selected the parts. They're also good and bad, but also that is more underwhelming. So let's do something a bit more wider and say, let's look at those pairs through all the stations. And now recalculate. And now I have one thing that is coming up in station 1. So in the very first station of my overall process called exposition. And obviously, there is a difference here because you see blue is in the bottom, red is on the top. When I go here to exposition, it just flips. So there is some kind of counter function in between those two. Maybe it's just a candidate, But the first thing that comes into my mind is, yeah, maybe those two correlate, then it's easy, right? So we take this one as an X, we take this one as a Y, and then we run a linear regression. And even though this looks really strange because there is some kind of step process here, there is no real correlation with it. So that's not the right method to use here. Still, something is going on. So let's look at it in a different way. I keep that the Y and I use that also as Y, and I run a multiple Y run chart. And in a multiple Y run chart, let's take out the marked points. Maybe it's easier to see it then. And do this multiple Y run chart again. Still not much better, so I change my limits here. I say I want to now have here from, from 0, and here I want to see all the until 0.12. Save, yeah, much better. And there's clearly something going on, specifically in that area where my suspect point or suspect part came from, where when it reaches a certain level below, what is that, on the position 12 point something, there is an increase in the working current. And that is now our root cause suspect. This is now where we go into the testing phase and see if we can reproduce that and flip it in order to turn it on and off. Once we have done that, we have confirmed the root cause. And now what we do is we need to control the position up here. So that's the next station then to work on. So that's the finding, but there is several ways how we could have gotten here. We could have used the group analysis here. We could have used the Y output, which is another functionality I'll show you maybe on the next webinar. But funny enough, the information was already here in the special event search. And here you see how powerful that tool alone is already. And this is how you use RTM for complex problem solving. So now that we have solved the problem, let's talk about celebration. And as a celebration of RTM, we'd like to invite you to participate in a so-called RTM challenge, to join us for a workshop in Cadiz. And the only thing you need to do is you need to share your own success story with RTM Pro. And we will evaluate that and invite you for a paid trip to Cadiz in order to conduct the workshops and exchange with the development team and our, let's say, application team to see how we can further improve our cooperation. So join us for the workshop. The winner gets the training and for sure also some very, very nice experience in this beautiful part of the world. So if you do not have RTM available on your on your computer in your work, then please request a free demo. We will then be able to provide you with a free, let's say, 30-day license. The demo database that I just presented to you is already integrated within RTM. So without integration work, without fighting with infrastructure, you can already start using RTM. You can already be trained in the basic functionalities and then benefit right away the moment you upload your own data through the several possible interfaces that we provide for RTM. And if you have it already, or even with the demo, feel free to participate. And I really look forward to then see you in Cadiz for our workshop of RTM. Thank you so much for joining in. It is an absolute pleasure to present to you RTM today and all its benefits. And I really look forward to see you in the next webinar. Bye-bye. See you next time.